Okay, in this video I will give you a quick introduction into how to use Simulink to simulate a transfer function. Okay, the first thing we're going to do is we're going to open Simulink with this clicking in this button, and it shall initialize. Then we create a new blank model. It takes a second. And now we open the library browser, which is here. Okay, here we can see the Simulink libraries where the different blocks are contained. We are going to use the continuous in order to add a transfer function block. Okay. Then we need an input for our system. Then we'll go here to sources and maybe use, let's say, a step input. We drag and drop it here, and then we'll use a sync a scope in order to visualize the response of the system. Okay, so we just put them together and we join them, connect them. Okay, so in order to introduce the parameters of the different Simulink blocks, we have to double click them. Okay, for the transfer function, all we have to define are the coefficients of the transfer function. So say I have a transfer function that goes like this: 1, 5 in the numerator and 1, 2, 1 in the denominator. And if I expand this, what you can see is that what I introduce are the coefficients of the polynomials, both in the numerator and the denominator. Okay, so let's just simulate a simple first order system. Let's say it has a gain 10 and a time constant, say, of I don't know, maybe 2. Okay, and now we have our transfer function. The step block, it has 3 parameters. The step time, that is when the signal changes from its low value or from its initial value to the high value. Let's say we want it to happen at 1.5 seconds. This is the initial value. Let's say we want it to start at 0, and we want the final value to be, say, 5. So we hit apply and OK, and then we just click run. When the simulation is completed, we can double click here in order to see the results. And as you can see, we see the response of a first order system. Notice that it doesn't quite reach the steady state yet because of the time constant that I chose, and when I chose the step to be performed, I need some more time to see all the curve. So that is easily done, just changing here the simulation time. Let's say we want to simulate 20 seconds. I hit play, and now we can see it's fully developed. Okay, there is one thing we can do, is that we can, instead of defining the coefficients of the transfer function directly in Simulink, we may want to define them in a script. So we can click on new script, and we define, say, we want a k of 5 and a tau parameter of, say, 2. We run it and it will ask for a name. We can say parameters. Okay, we save it. Okay, and now here in the workspace we already have the values k and tau, and we can use them in order to define the parameters of our transfer function. So here we say k, down here we say, sorry, I want it to be k, and here, down here, we want it to be tau. So we apply, we say OK. It will tell us that what the transfer function is, and it's OK. Now say we want to model a transfer function for a mechanical system of mass, damper, and spring. So let's define, say, the mass. We want it to be 1 kilogram. We want the damper to be 0.1, and say we want k to be 2, for instance. Again, we run, and all we have to do to simulate the system is just define here the model of the transfer function. Here in this case it's 1 in the numerator, it's the mass times s squared, b times s plus k. So yeah, small k. So we say okay. Again, if we expand this, we should be able to see it, probably. Yeah. So we can just move this a little bit to the left, this a little bit to the right. Okay. And we can simulate. Now we simulate and we see the response. Notice that what we are seeing here is that this response is not really neat. We see here the points are joined by straight lines, and we don't really like that. We can change that here in modeling, in model settings. Depending on the version of Simulink that you have, it will be in one place or another, but it's always represented using this kind of wheel. Okay, so we use that, and here in solver details all we have to do is just increase the relative tolerance, say 1 to the minus 7, and the absolute as well. We apply, we say okay, then we run again, and now we have a cleaner solution. Now as before, as you can see, it has not reached the steady state yet, so we can just increase the simulation time and see. Okay, it has not yet, so we can still increase it a bit more if you want. This system is very lightly damped, so it takes a lot of cycles for it to finish the oscillations. Okay, so that was all I wanted to show you in this video. I think that with this information you should be able to do the lab session 4 with no problems.